Industry 4.0 is associated with numerous keywords. For about 10 years, there has been a very comprehensive discussion about how industrial work can and should be redesigned with the help of Industry 4.0. Many of the ideas discussed have not yet come to function, but the core of Industry 4.0 production is automation, and as a prerequisite for automation, production is being organized in a leaner way as before. Keywords which are used around Industry 4.0 are changes in industry, paradigm change, disruption, digital technology, lean production, Industry 3.0, and 4.0. The discussion about these terms and about the term Industry 4.0 started in 2011 at the Hannover Messe in Germany. Industry 4.0 is a broad field in which digitization technologies are increasingly being applied. This expansion by digitalized products leads to new uses of technology with a diverse influence on our daily lives. It is therefore advisable to keep an eye on so-called guiding questions, in addition to taking a closer look at the various developments. Answering these questions opens the perspective for the broad and diverse development of Industry 4.0 in combination with digitalization. Answering the questions clearly shows that our entire lives as our actions are influenced by the development of digitalization. These questions will not only be discussed again and again in Module 1, but also in Module 2 and in Module 3, an attempt will be made to provide answers to these developments in the curriculum design. What is new about Industry 4.0 and digitization? The new thing is the networking of cyber-physical systems, CPS, with conventional machines and the internet. The machines, the physical objects, are connected to the Internet of Things, IoT, with the help of the cyber-physical systems and exchange data on the operation of the machines and systems. This data is in turn used to optimize operations. Cyber-physical systems are intelligent objects that connect passive devices and objects such as machines to the internet. That is, they network them. This overcomes the communication gap between the individual machines and the technical networks and ensures the exchange of data with the help of CPS. The exchange of data itself takes place via digitized signals, ones and zeros, as has been known for several centuries. In this context, the question naturally arises as to who the real drivers of Industry 4.0 are, which products contribute to the spread of Industry 4.0 and digital technology. The answer is relatively clear in this case. On the technological side, it is robotics and artificial intelligence. And on the data and data exchange side, there are storage elements such as clouds and the Internet of Things. Robots are assets that can perform a wide variety of tasks, and it is relatively easy to control them via programs. Artificial intelligence supports program controls and the definition of algorithms to design operations, and the Internet of Things supports data exchange between assets and networks. Cloud computing is used to store huge amounts of data. A very frequently asked question is, what is changing technologically as a result of the application of Industry 4.0? The preceding remarks have already shown that various technological components and systems are growing together via networking. That is, they are becoming increasingly integrated. This is why there is often talk of technological convergence. As a result, process flows are less interrupted by technological interfaces and can be designed end-to-end, which is an important contribution to intensifying automation. The data transfer that is possible between products, between plants, between parts of a company, and different company locations as a result of increasing networking is possibly one of the most profound changes. The availability of data also lends itself to monitoring production and the production processes, using data to control them directly and without human intervention, which contributes significantly to increased autonomy of manufacturing operations. This situation requires management structures and the assumption of responsibility at the shop floor level, for example, which has never been the practice in companies before. As already mentioned, the fourth industrial revolution also has implications for the design of education and competencies that we humans will need in the future to deal with the new technological structure and work organization. Education and also vocational training must of course deal with technological changes and also changes of work organization. In this context, it is particularly important to clarify how work structures in industry will change and what knowledge and skills are needed among skilled workers to cope with the new challenges. For vocational education and training, it is particularly important to clarify the question of which work structures skilled workers below the academic level need to be prepared for and which competencies they need to have. This means, of course, that curricular issues need to be clarified in this context. A further question is how education and training processes are to be designed in order to adapt to the new situation. From a socio-political point of view, digitization entails that the connection between technology, work organization, and qualification levels become more and more important for companies. When designing work structures, these three pillars must always be considered in conjunction with each other, because every change has an impact on requirements, right down to psychological consequences such as workloads and the efficiency of the economy, and much more. Thus, professionals are no longer confronted with simple technological products, but companies are increasingly becoming a reflection of complex social structures. Teachers have to be sensitized to this situation because their target groups are confronted with this situation on a daily basis and can also take creative action. The current development of digitization and Industry 4.0 has a broad impact on the need for skills. So far, it is not yet clear which key competencies are of particular importance. Therefore, three theses are formulated, namely, thesis of high qualification. This assumes that cognitive demands will increase and therefore higher, especially academic educational qualifications, will be necessary for working life. Thesis 2 assumes that polarization will take place. After that, simple tasks will be automated, which means that skilled workers will no longer need to be qualified for them. Thesis 2 assumes also that especially well-qualified specialists below the academic level will be necessary. In other words, people who should not only have enjoyed standard vocational training, but also have already gained experience in modern production. The third hypothesis assumes that the level of qualification in industry as a whole will increase. It is assumed that this will lead, above all, to more academically qualified people being needed for industry. Because academization plays a major role in the discussion, it is pointed out here that, for example, classic tasks such as welding will still play a major role. Of course, Industry 4.0 is contributing to welding robots being used for this. The question, however, is who will program the welding robots? A computer scientist or a skilled worker who is trained as a welder? The answer is relatively simple. For the welding tasks, a robot must be programmed by skilled workers. In other words, the programming must be as simple as possible, so that skilled workers without academic training are able to program these robots according to the tasks. The Industry 4.0 Skills Radar shows how comprehensive the discussion about skills profiles is. This was created on the basis of several studies in the European labour market. It shows a wide range of competencies and skills that could be expanded. However, it is essential that context-related competencies are also taken into account. These are the core of a skilled worker's activity. Without the broad abstract competencies, however, skilled workers are not sufficiently qualified. This means that the skills radar provides a helpful overview of the necessary breadth and depth of skills that skilled workers must possess. The focal point of digitalisation presented so far already clearly show that it is not just a matter of technological development, with the help of which productivity in companies is to be increased. At least three other components are central elements of development. An improvement in the flexibility of the production method, greater speed in product generation and improved quality. This aspiration has implications for all fields of activity, such as innovation, safety, worker conditions, sustainability, and training. Teachers must keep this diversity in development priorities in mind when training professionals for industry.